Hello everyone, my name's Don Woodlock here at InterSystems, and I'm going to talk about machine learning today. And what I'm going to focus on is how it actually works, because I'm sure you've heard of it, I'm sure you've seen all the hype, I'm sure you've seen that it's going to solve every problem imaginable, and I've seen that too, but none of the articles that I've seen or read have really explained how it actually works, and it's not that complicated. So what I'll do is walk you through how machine learning actually works with a couple examples, and hopefully you'll enjoy this. So first I'll add to the hype. This is Google's CEO saying AI is more important to humanity than fire and electricity, which is kind of an amazing statement. So I'm also enthusiastic about AI, but it certainly is at the top of the hype cycle now. But it is an important thing to learn about and to put to use in our software going forward. So hopefully this will inspire you to do that. Okay, first I'll cover a slight definition of terms, and then we'll get into it. It's just basically a simple Venn diagram. So artificial intelligence is the broadest term, and this refers to basically teaching a computer to do something that you would think only a human could do. So an example of AI that's not machine learning would be how computers initially played chess. I don't know, calculating sort of trees of moves and pruning the trees, and depth first searches and things like that to sort of choose the best chess move. So that was AI, but not machine learning. So machine learning is what we'll talk about today. And then there's a subset of machine learning called deep learning. And I will not have time to get into that in this session, but a lot of what I'll talk about also applies to deep learning. And deep learning takes it one step further, which if I do another session, I'll tell you all about. But deep learning is used, especially with images, but is being put to use across the whole machine learning spectrum as well. Okay, so what's neat about machine learning is a lot of computer science, the last, 40 years or so, has been new programming languages or databases or things like that, but essentially solving problems the same way, or variants of the same way. And machine learning is a very different way of solving a problem. So let me give you an example. So if I were to ask you to write a program that tells an adult from a child, and I was only going to tell you two things about the person. One is their height, and second is how much money they have in the bank. So the question is, how would you write that program if this was your job? What you typically do, or what we have done for decades, is we basically ask somebody that knows, a subject matter expert. So you might ask a pediatrician for average heights of children and average heights of adults. You might ask a banker, what are some of the statistics about how much money people have in the bank by age, things like that. And then you'd write a program that sort of codifies that subject matter expert, in a sense. So a program with a lot of if-thens, if it's less than this height, or if the money is this much, do this, make this choice, otherwise make this choice. So essentially you have interviewed subject matter experts, and you've codified their knowledge in your logic. So that's the traditional programming method. And we do software for physicians and for nurses and for finance folks and what have you. And it's that same thing. You're trying to understand what they're thinking, what their subject matter expertise is, and codify it in the way they want to see it. So machine learning is not that. So essentially, instead of codifying the knowledge in the system in a complicated algorithm, you write a generic algorithm and you just feed it data. Okay? So you feed it data, and it's going to generate the rules based on the data, not generate rules based on interviewing the subject matter expertise. So you can see in this slide how it's a different approach where data runs into the algorithm and the rules come out versus rules running into the algorithm that codifies that, and then the answers come out. Okay? So let's dive into this problem of an adult versus a child. So I'm going to go to the board here. And let's say I have on this axis I have the individual's height. And then on this axis, I have the money in the bank. Okay? And then what I'm going to do, let me find my black marker. What I'm going to do is put an X where the adults are and an O where the children are, okay, on this 2D surface. So where would you expect to find the X's? Where would you expect to find the adults? The answer would be kind of on the top right. They generally have more money in the bank. So if I would graph all the adults, and they're generally taller. So you may have some individuals that don't have that much money that are adults, and you may have some adults that aren't that tall. But generally speaking, they're kind of tall and have money in the bank. And then the children, conversely, will be shorter on average and have less money. So they're going to be down here. Okay? You may have some children, and maybe a child is 14 or under or something like that, because 18-year-olds can get tall. But you may have some children that have a lot of money. So they might be out here. And you may have some tall children, reach 6 foot by age 14, something like that. But by and large, you're going to have the children in one part of the space and the adults in the other part of the space. So the question is, could you write an algorithm that really separates these points? Okay? So when you're given the next person, you can use that algorithm to generate whether it's going to be adult or a child. So that's what machine learning does. Now, a lot of these algorithms, you won't believe it, are very simple in that they separate the data points by a line. So you can see if you had a line something like this, that you're basically, for the most part, separating the adults from the children just by finding a line that best kind of separates these two classes. Okay? So that's what machine learning might be, that you feed it this data and it searches for that line. So let's remember way back in grade school, I think, what is the definition of a line, or what is an equation for a line? And I'm warning you, there's a little bit of math in this particular session. So the equation for a line, if you recall, is y equals mx plus b. That's the most common way we learn to write a line if we know the slope and the y-intercept. There are other ways to do it. If you have 2 points, there's ways to organize a line, but this is one way to write it. Now, I'm going to mess with this equation a little bit, but it'll still be the equation for a line. So you can, for instance, instead of y and x, I'm going to have this axis be x2 and this axis be x1. Okay, so you could say x2 equals mx1 plus b. So it's still a line, no problem. Now I'm going to move everything to the left of the equal sign. So you have x2 minus mx1 minus b equals 0. And then there's 3 constants. There's a 1, a minus m, and a minus b. And I'm just going to change the letters around and kind of redefine them. And you could write the equation this way. W0 plus w1 x1 plus w2 x2 equals 0. So that is basically still the equation for a line. It's just written in a different form. The reason I write it in this form is this is the way we like to see it in machine learning, because the x's stand for the features. So the features of each instance, in this case, is height and money in the bank. And the w's stand for the weights that get multiplied by each feature. Okay? So essentially, the trick here is finding the weights that represent this particular line. Okay? And you can also see that this could have more than 2 features. So one of the, obviously in machine learning, you might have data sets that have lots of features about a patient or about a recipe. I'm doing a contest around categorizing recipes, things like that. You might have thousands of features or tens of features, something like that. But the equation is the same. You have a linear equation with a bunch of weights multiplied by a bunch of features, and you set it equal to 0, and that is the line. Now, this is referred to as a line in 2 dimensions and as a hyperplane in other dimensions. But it's the same idea, that you expect the data points to be separated in a different part of the space, and then an equation that actually separates them. And the way this equation works is if you evaluate the left side, if it's greater than 0, it's going to be one side of this line. And less than 0, it's going to be another side of this line. So you basically just have to run the equation and compare it to 0, and then pick the one class or the other class. OK? So, so that's essentially what the machine learning algorithm will do, is take this data and search for the weights that best separate the classes. So let me describe how it does that. So today I'm going to go through 1, 2, 3, 4, 5 of these algorithms, actually. And the first set are linear separation, just what I'm talking about here. And the others are a little bit different approaches. But we're going to start with the very simplest one called a perceptron. And I know I started with the adults versus children, but now I'm going to jump into one of the most popular, it's basically the hello world of machine learning. And it's a data set called IRIS, coincidentally called IRIS. And it's a data set of flowers. So let me show you what that looks like. So this is a data set. And I'm going to start out with just 100 rows of the data set. 50 are a flower called the Iris setosa. And then the other 50 are a flower called the Iris versicolor, or versicolor, something like that. I actually don't know flowers, but OK. And then for each flower, you have 4 parameters: sepal length, sepal width, petal length, petal width, and that's it. OK? So that's the data set. So let me head back here. So let's take a look at it. What I'm going to do is I just picked 2 of the features because you can graph 2 features. If you have more, you can't really visualize it. So you see the petal length and the sepal length. And you can see the 2 flowers. And you can see that these are, just by these 2 parameters, linearly separated. One parameter would do it, but we have 2 parameters here. And you could see that they're separated in this space. So how would you write a machine learning algorithm to basically find those weights automatically by feeding it these 100 flowers? Well, I will show you. Next on this. OK, I'm going to start with the simplest algorithm called the Perceptron. And the way it works is it generates initial weights randomly. So it just picks a couple weights. Then it runs through the data. And then with each, a bunch of times. So it's actually going to run through this data 50 times is the program I'm about to show you. And then with each row, it's going to calculate the flower. It's going to calculate the left side of this equation. Remember, it has randomly generated weights, and it has the features, 2 of the features for each row. So it's going to generate that row, and it's going to come up with a number that's greater or less than 0. Okay? If it's greater than 0, it's going to be 1 flower. And if it's less than 0, it's going to set it to the other flower, essentially. And in this case, the flowers are 1 and -1, because these equations like numbers. OK, so if it's correct, so if it guessed the flower correctly, it's going to leave the weights alone. And if it incorrectly guessed the flower, it's going to adjust the weights slightly in the direction of being right. So for instance, if it guessed -1 and the flower was the 1, it's going to move it more positively toward the 1, or vice versa, basically. And then it's going to do that 50 times in this case, and keep adjusting the weights. So it kind of draws an initial line, then it keeps messing with the line as it keeps churning through this data set, and then eventually it stops, and eventually the weights should be better than the random ones. So This is not really a code review, but I'll just show you the code anyway, because it's only 18 lines of code, basically, to do a perceptron. So it's not like the most complicated thing in the world. So what you have is, this is Python, by the way. The top section is this is a class, so it's the model itself. So you're instantiating the model, and the top part is the constructor. So eta is it's the Greek letter, and it's basically the learning rate, or how much you're going to nudge the weights each time. We're going to go through 50 times, and then random state is just to help with the random numbers. And then fit is the main method, and fit takes 2 arguments. X is basically this. So this matrix is X. So it's an array of arrays. So each element of the array is an array of these 4 features. And Y is this, basically. So it's an array of the labels or the classes, stated as 1 or -1 in this case. So it's actually a number. So that's what that is. OK, so what we do is we randomly generate the weights. Those are carried in a property called W underscore as an array. For each of the 50 times through, for each flower, it grabs the features and the target class from X and Y. And then it does an update. And what it does is it takes the target, so what is the actual flower, and then subtracts the predicted flower. So if it got it right, then update ends up being 0, and the weights aren't adjusted. And if it got it wrong, then this part will be either 2, 1 minus -1, or -2, -1, -1. And it'll adjust the weights slightly based on this eta factor. So the weights are adjusted. The weights are left alone if it's right, and slightly adjusted if it's wrong. And this is just the calculation of the left side of the equation. What this is you can see it's a matrix. So you have a matrix of weights and a matrix of features. And it just does what's called a dot product. Multiply each weight by the feature, and then add them together. So that's why it looks like that. So it's a dot product of x, of xi, actually. It's passed in as x. And then the weights, and then you add W0 on the front. And then you compare that with 0. And if it's positive, you do 1. And if it's negative, you do -1. That's essentially, and that's it for the code. OK? So let's see how it does. All right, so it did the job, basically. So that line you see is the line that the Perceptron, so that was the real code running those 18 lines, 50 times through this data set of 100 flowers. And it generated these weights from its initial random weights, played with them, by adjusting everything. And that's the line. And you could see it did a perfect job from a separation point of view. All the flowers of one class are on the top, or in one region, all the other flowers in another region. It found the right weights. So that's machine learning, basically. I'm going to go through a bunch of other algorithms, but that's an example of a very compact and a working algorithm, basically, to kind of generate linear separation. Let me show you just one other view of the equation, because I'm going to make this a little bit more complicated later on in the presentation. So essentially, this is just the equation written graphically, in a sense. So it kind of adds a 1 here. So it pretends like the first feature, like an x0, is a 1. And that allows a clean matrix multiplication of w and x. So you can see the w's are multiplied by the x's. They're added together. That's the dot product. And that's the net input. That's what this is, the left side of the equal sign. And then it runs through a threshold, meaning is it greater than 0, set it to 1. If it's less than 0, set it to -1. That's what that function is. And then adjust. If there's some kind of error, go back and adjust the weights slightly. So that's what we just saw in the code, and that's kind of what I just explained. Okay, so just a couple nuances. This one I've covered. So what if you have more than 2 features? No problem. So you could have, actually in this iris data set, there's actually 4 features. I only ran this model on 2, so you could visualize it, but you could run it through all 4 features. So there'd be 4 X's, there'd be 5 weights, no problem. Some models might have 100 features, but it's no problem, and the whole thing works the same. It generates 100 weights. It plays with the weight factors by running through the data set and adjusts them until you have these things separated. Okay? So the number of features doesn't matter algorithmically. It only matters in terms of your ability to visualize it and in terms of how long the training process takes. What if you have more than 2 classes? So, so the way machine learning algorithms handle this is this concept of one versus rest. First of all, this data set actually has 3 flowers. So I made it simple to just take the first 100 rows, but the data set actually has 150 rows, 50 of each flower. And what it does is it trains 3 models. It trains the first flower against the rest. Then it trains the second flower against the rest. And then it trains for the third flower against the rest. So it's called the one versus rest. So it trains it 3 times, basically. And that's it. And then it'll just pick for any given data point. It'll pick the flower that has the highest score, the highest kind of number, positive or negative, or positive, I should say. So the highest positive number picks that flower. So let me show you what that looks like in this case. Okay, so this one, not to confuse you, I think we changed the 2 features that we chose to be slightly more difficult because that other one was super easy. It was very separatable. And this one has a little bit of complexity where it's not perfectly separatable, as you can see. But you can see how the one versus the rest works. It's basically training the red versus the rest to come up with a line. It's training the X's versus the rest to come up with one of the other lines. It's training the circles versus the rest to come up with one of the other lines. And there's various tiebreakers where they kind of intersect. But it generates these 3 lines and then puts them together. So that's how more than 2 classes are done. The other thing you'll notice in my screen here is that this is 93% accurate. So how do we know how accurate a model is after we've trained it? Well, you can't actually run the training data through actually, it's unfair to run the training data through the model that you used, if the data was used to train the model, because that's not the point. The point is to build a model that performs well with unseen data. So you want the 151st flower. You want to know how accurate it's going to be to predict that flower and the other 200 flowers and the next set of flowers. So essentially the way we do this in machine learning is we take part of the training data set, like 20%, and we set it aside. And we train the model with the other 80%. And we don't let it see the 20%. That would break the rules. So we just train it on the other 80% and then run it against the 20% and then calculate the accuracy that way. So that's what you see here, is that this is 93% accurate. And actually, let me look at the picture again. I can show you. The ones that are in circles are the test set. So you can see, you can probably find them. There's 3 samples that were miscategorized. 1, 2, 3. So that's where it got the 93% accurate. Okay? All right, so that is the Perceptron. That's just the starter model. That's easy, not that many lines of code, just gets you kind of warmed up. Now, logistic regression is one of the most popular models, and it's actually not that harder. And it's an extension of the Perceptron idea. And you can imagine, as machine learning has been going on through the years, this sort of built onto the the strength of the perceptron and just added some sophistication to it. So this is what it does. So logistic regression, the key thing about it is it predicts the probability of being part of the class. Not just what flower does it predict. It predicts both the flower and how confident it is that that's the right flower. Okay? So and this is very desired sometimes. So for instance, if you wanted to predict whether it's going to rain or not, that might be useful, a yes/no answer. But what may be more useful is the probability that it's going to rain. Okay? So you can write an algorithm that says, okay, if it's over 50%, draw a rain cloud. If it's under 50%, don't. But you can even change that percentile to be whatever you want. So it's more flexible in that it gives you a probability as its answer, and then you could decide on the threshold that you're going to use to decide on whether it's part of the class or not. So that's a very useful thing. The way it does the probability is if you think of the left side of this equation, this can be any number. A big positive number, 5, 50, 5 million, a big negative number. There's no really bounds to this. What it does is it adds one more function after the net input, which is that thing, to squash it between 0 and 1. Okay? So you can see it down there. It's called the sigmoid function, basically. And the position here is called an activation function. So after you calculate it, you squash it between 0 and 1. So big negative numbers become close to 0. Big positive numbers become close but just under 1. And then halfway in between is 0.5, basically. So it kind of squashes everything down to 0 or 1, 0 to 1, and then you could use it as a probability. And you could decide, again, is my threshold 50%, to decide, or something else. So that's one essence of logistic regression. The other essence of logistic regression is it has a more clever way of finding the weights than just nudging them, the same amount each time. And it's called gradient descent. And let me describe that. So before I write here, so one thing about logistic regression is it's common to run all the data points through before adjusting the weights. So if you recall, in the Perceptron code, every row, we would adjust the weights. Calculate, adjust, calculate, adjust. This one, we run the whole data set through one time, calculate the total error, and then adjust the weights accordingly, and then run the data set the next time, calculate the total error, which hopefully is less, and then do a weight adjustment. So we kind of do it in batch. And this speeds up the training time, actually. And it has a couple other qualities. But imagine you have a calculation of the total error value. And maybe the way you think of this, let's look at this spreadsheet for a sec. Maybe you think of this as you have your target, which in this, let's say we're training for iris setosa. In the one versus rest idea. And iris setosa is 1. The probability of it being the iris setosa, if it is the iris setosa, it's 1. And if it's not, like down here, we'd have a bunch of zeros. And then you have your guess. And that guess is going to be a number between 0 and 1. So 0.8, 0.2, something like that. Okay? So your error is going to be this number minus this number, something like that. And you might square that or something like that to make sure it's a positive number. So you have some way of calculating your total error. So the sum of this column, and it might be your the sum of squared errors, something like that. And then you have your weight. Just pick any particular weight. So let's say weight number 1. So we want to find the perfect value for weight number 1, right? As well as finding the perfect value for weight number 2, etc. So what you might think of it as you want to find this value for weight number 1, that has the smallest total error value. It won't be 0. It would be hard to get everything perfectly right, like all your guesses to be 1s and 0s. But it's as low as possible. And if your weight is too high, then your error will be greater. And if your weight is too low, then your error will be greater. So essentially, you want to find the bottom of this hill. Okay? So how might you do that? So so imagine this. You have an equation for total error value, and you have a weight. So it's an equation as a function of this weight. Now, do you remember from, maybe this was high school, maybe it's 8th grade, depending on when you took calculus. Do you remember how to find the minimum of a function like this? So the answer is that you take the equation and you take the first derivative of it, and then you set that equal to 0. So it's essentially the slope. The first derivative is the slope at any given point. And what you want to find for a u is where the slope equals 0. That'll be your lowest point. Now, you can't just solve it that way. Because that would seem logical. That would give you the perfect weight number 1, is you take the first derivative of the equation, you set it equal to 0, and then you find the value of W1. But the reason you can't do it is, the best analogy I can think of is the way you might tune a guitar. Now this isn't a perfect analogy because we don't do it this way. But for those of you who play guitar, if you pick up a guitar that's like really out of tune, and then you take the first string, the E string, and you tune it to a perfect E. And then you go to the next string and you tune that to a perfect A. What happens to the E string? Turns out the E string is a little bit out of tune. And that's in the guitar's case, that's because the neck bends a little bit as you tighten the strings. So all of a sudden the E is a little bit out of tune. So the same thing with the weights. If you get the perfect W1, then when you move to the second weight, it's going to make the first weight no longer be perfect. And so on. When you go to weight 3, you have to go back to weight 1 and weight 2. So essentially what we do is instead of trying to find the perfect weight, we just move toward it. So we move our way down the hill to get to the bottom, but we don't try and jump straight to the bottom. Okay? But what we do is actually we take a look at the slope. So you do this first derivative. You get an answer for the slope. And the slope will tell you two things. One, which direction to move the weight. So if the slope is positive, then you can move the weight to the left. And if it's negative, you're going to move the weight to the right. Okay, so you know the direction down to the bottom of the hill. And the second is you know how much to move it. So for instance, if you're up here, you want to move the weight a lot. And if you're down here, if the slope is pretty small, you want to move the weight just a little bit. So it's a smarter way, using this error value equation and using the first derivative, to adjust the weights. Okay? So that's essentially what logistic regression is all about, is you train in batch and you use what's called gradient descent to kind of step your weights down to the bottom of the U as fast as possible. Okay, so that's why it's a popular algorithm. It's fast, it's good, it's accurate, that sort of thing. So let me show you what logistic regression looks like on our data set. Okay, so this is the Perceptron. This is what we saw before. And this is logistic regression. So you can see that the lines are different. And I'll show you in a moment that logistic regression is more accurate, actually. So it does a better job with separating out the different classes. And because of this smarts, it actually works faster because it's smarter in the way it approaches the bottom of the hill. And you can actually see, if you look at my little command line terminal program here, that's actually 98% accurate. So the Perceptron was 93. Logistic regression is 98. So it's very good. Very good indeed. OK. All right, so that is logistic regression. This I already talked about, how you evaluate a model. So you set aside some of the data, you train your model, and then you run it on the set-asides. And you're not allowed then to retrain the model based on what you came up with. That has to be just test data that you use to evaluate your model accuracy. OK, so I'm skipping over a few, which are similar in that linear separation is the main concept. So now we're going to go into some algorithms that don't use linear separation. So the first is a very popular algorithm called the decision tree. And the way a decision tree works is, I'll show you it on the graph. It does not use an equation. So I'm going to erase the equations to not confuse you. What a decision tree algorithm does is it picks one of the features. So let's pick money in the bank. And what it does is it picks a line that best separates one class from the other class. So it's not going to be perfect, but it kind of walks along. You know, should I put a line here, 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 and then finds what it considers the best separation line. And it just draws it. So it's probably right here. OK? And then it picks another feature. It picks one of these areas, which it considers to be the most impure from a classification point of view. And then it takes another feature, and it draws another line based on where the separation would be best. So let's say it works on this quadrant, and it's going to pick height, and it's going to say, well, if we drew a line right here, that would be a good separation for this section. And then it does it again. So it might say, OK, this is the next most impure section. I'm going to do height again, and I'm going to draw a line here. And so essentially, it's building a if-then decision tree. If the money in the bank is less than this number, then I go down this path of the tree. If it's greater than this number, I go down this path. And then it builds the next layer of the tree. And I'll show you exactly what this looks like. So it's basically it's almost generating the if-then logic that I was referring to in the beginning, but using the data instead of asking a subject matter expert. So let me show you what it looks like on this data set. OK, so you can see how it worked. It drew a line, probably drew this line first, this horizontal line, and I'm sure it was quite happy. It got all the red flowers on one side, and that was a good separation. But obviously, the other two colors not so good. And then it drew one of these vertical lines next. Then it drew this horizontal line, and then it drew the other vertical line. And it does pretty well. You could see it kind of separates the points. And what's important about this is actually, as I failed to mention a few minutes ago, sometimes you can separate out these classes, but not using linear rules. So sometimes the way the separation works, it might be like all the one class is in the middle and all the other classes on the outside, or all the one class is here and here, and all the rest are down here. And so sometimes you can see the separation, but it's not a line. So the beauty of decision trees is it can work with nonlinear separatable data. Okay? So when you have data that can't be separated by a line, you throw a decision tree at it, and a decision tree is much more flexible in terms of breaking out the data and separating the different classes, as you can see in this model. So you're not stuck with just one line or two lines in this case. You can draw a bunch of lines. Okay? So let's see. The other nice thing about decision trees is you can actually see the tree after the model training is done. So here you can see it did the split on petal width first. Less than 0.75, go here. greater, go there. Yeah, that was right. In this case, it's setosa if it's less than 0.75 and no more logic. If it's greater than 0.75, I might be saying all that backward, but you know what I mean. If it goes down this section of the tree, then it looks at petal length and breaks it into two. And this essentially is the decision rules of the graph that I just showed you. The other benefit of decision trees is this concept of explainability. So one of the big problems with machine learning today is that the algorithm, you can't explain why the algorithm does what it does if it's just a bunch of weights. So for instance, let's say you had a machine learning algorithm that predicts whether a patient is going to get diabetes in the next year. Well, if a physician asks, well, and the algorithm said, yes, this patient is probably going to get diabetes in the next year, and the physician says, well, why do you think that, computer? And all it has is a huge list of weights to show you it's not that explainable. Or, for instance, if machine learning, which it is used to drive self-driving cars, and a car runs over a pedestrian, and everybody in the courtroom or the town or whatever wants to know, why did that car make the choice? Why did it turn right when it shouldn't have? All you have is a bunch of weights with the linear separatable algorithms. So in this case, there's a little bit of explainability here. The model itself has some logic that you can kind of follow, right or wrong, and it can explain itself a little bit better than the linear separation model. It's not quite perfect, but this is a relatively big problem in machine learning that a lot of people are working on, is explainability, because it can hold the field back if the whole thing is like a mystery, a black box concept. So that's another nice thing about decision trees, is this explainability concept. Okay, so what I'm going to do is now talk about random forests. And a random forest is a collection of decision trees. So you might have noticed the name, the tree and the forest. So basically, you randomly generate a bunch of decision trees, and then you kind of add them together to determine your answer. And so let me describe the technique with this question. So if you have, let's say, a team of 9 people, and each person is 75% right, okay? So you ask them a question like, should we build this new product, let's say? And each person is, pretty good. They're mostly right and 75% right, and they all give you an answer. If you majority vote their answers, so meaning you take whatever 5 or more people said. Remember I said there were 9 people, so you take what the majority said and you go with that. How accurate do you think you would be? So the answer is you'd be 95% accurate. So because most people are right, most people are 75% right, and you're sort of adding them together, and the odds that 5 or more are going to be right is actually 95% in that case. So it's actually an amazing concept where you take raw ingredients that are only 75% right, but you combine them together and you get a better algorithm, essentially. So that's what a random forest is we randomly generate decision trees, and then we majority vote them basically for an answer. Okay. The other thing to point out is each of the members, like your 9 people, need to be completely independent. So independently 75% right. So for instance, if the boss is in the room and everybody just listens to the boss, then as a group of 9, you're only going to be 75% right because you're basically being influenced by each other. So the idea is the models have to be completely separate. And decision trees in this random forest uses different techniques to make it randomly separated decision trees. But that's really key. They have to be separate models. If they're somewhat correlated with each other or somewhat use similar information, you're not going to get the exact numbers that I gave you. Okay, so let's take a look at the results of a random forest. This is the decision tree, the one we just saw. And this is the random forest. I forget how many decision trees we used, but essentially we're sort of averaging multiple decision trees. And you can see this is a more complicated, more complex picture, but it can be more accurate. So you have a little bit of working around nooks and crannies here that sort of helps the accuracy in this case. So that's kind of what the random forest looks like, a group of decision trees. The random forest, okay, you can see it on my screen here. The decision tree was 98%. The random forest actually didn't add that much, or didn't add anything at this number of digits. But that is quite possible because the accuracy is so high. There's not a lot of room to go from there. Okay, and actually, let me put that later. Actually, for those interested, actually, I'm not even positive I got this right, but at my desk, I worked out this probability because I taught this class in front of a room yesterday, and I knew somebody would ask about the probabilities. But this is where I got the 95% right. It's basically 1 minus the chance of being wrong, which is the chance of 9 people being wrong, plus 8 people being wrong, plus 7 people being wrong, etc. So that's that. Okay, so let me cover one more algorithm, and then I'll basically close. So this is the k nearest neighbors algorithm. And what's interesting about this one is it doesn't learn at all, essentially. So it just takes the training data set and just leaves it there. And then when it gets a new point, it finds the 5 nearest neighbors, or the 9 nearest data points to that one, and then majority votes them. So k just means you have to pick a number, so pick like 5. So it finds the 5 nearest neighbors, and then it picks the majority of what those nearest neighbors are. So it's actually called lazy learning, and in fact, it doesn't really learn at all. It just when you get that next flower, it looks through the data sets of flowers, finds the closest ones to it. And by close, it's basically can be a simple thing as Euclidean distance. Like imagine everything is a number. When you put that point on this picture, what are the 5 points that are closest to that point from a distance calculation point of view, and pick the majority of what those 5 are. Okay? So let me show you what that looks like, and I'll make one comment about that. Where do I have that? Here it is, 3E. That is the random forest. And this is k nearest neighbors. And by the way this graph works actually is, you don't really see it, but it kind of runs all the data points through the model after it trains it, and then it just graphs the color. So that's how this program works. So it basically can show you the separation space. And graph it that way. But you can see the k nearest neighbors, as opposed to many of these other algorithms, is not straight lines at all. So it's more of a smooth decision surface between the different things, depending on where the closest points are. And it can be pretty accurate here. And in fact, in this case, k nearest neighbor is 100% accurate. So it got all the test points right. Now, it turns out it doesn't mean that it's better than the other ones. Otherwise, we would just have one algorithm and have dropped the other ones 20 years ago. But nevertheless, some data is better for some models, not others. Some data is linearly separatable, so you use those sorts of things. Some, there's just different, like text at the support vector machines, which I didn't really cover. Is very popular for that type of thing. And so different kind of problem spaces use different models. And you can also do an ensemble that combines them all together, and I'll show you that in a moment. But I did want to talk about k-nearest neighbors in one other way. So one of the ways k-nearest neighbors is often used is suggestion engines. So like you're on Netflix and it's recommending TV shows or movies that you might like based on your past viewing history. So the way it does that is it uses machine learning, as you might expect, but it's unsupervised learning. So what I've covered so far is supervised learning, meaning you have the answers. So we have this data set of flowers. Every row of the data set, we know the flower. Okay? So the classes are sort of predetermined. They are these 3 flowers. But with Netflix, what they can do is take all their customers, and you might have an algorithm like break this customer base into 10 groups. And basically, it'll randomly pick 10 points on the graph, if you picture a 2-dimensional graph, and then it'll cluster all the points closest to that 10. And it'll make 10 clusters of customers. Okay? So it almost generates the classes by itself. And then there's more sophisticated algorithms that'll sort of reset the centers of the 10 based on the centers of these clusters and run it again. But when the model's all done, you have 10 clusters, let's say. Okay? So essentially, these are like classes. So there might be the horror movie fans, or the Will Ferrell fans, or the romantic comedy fans, or who knows. They would kind of group customers together based on having similar features. And the features may be the things Netflix knows about you, account information like your age and gender and things like that, or address, zip code. I don't remember what Netflix knows about you, but certainly your viewing history. So the last 50 movies you've watched, things like that, are all the features that have led you to the cluster that you're in. And then what happens is when you log into Netflix, what it can do is show you the movies and TV shows that other people in that cluster have watched. Okay? So that's basically how a suggestion engine works, is it's clustering of customers, and then assuming, which is a fair assumption, the customers that are like each other will like things that the other ones have liked. Okay? So that's another use of k-nearest neighbors for unsupervised learning, where you're sort of clustering. But that concept of k-nearest neighbors is a very powerful concept, which is essentially used in the suggestion engine use cases. Okay? All right, so let me just show you one other thing on Ensemble. 7A. So you can see over my terminal here, ignore that warning, but you can see up here that each of the core models, logistic regression, decision tree, KNN, etc., had an accuracy of high 80s. But what you can do, I don't know why it repeats it 3 times or what have you, but what you can do is you can majority vote the models. So for any data point, you could run it across the 3 models and then pick the majority of what the models say. And you could see that ends up a majority vote with a 94% accuracy. So not only can ensemble techniques be used within decision trees to build a random forest, you can actually use them across models. So you can see here, this is 2 other features of the flowers. That's why it doesn't look exactly the same. But you can see logistic regression gives you one separatable decision tree. This is a very simple decision tree. KNN, and then a majority vote of all 3, and it has an even more accurate style. So this notion of combining models is also good. So you don't necessarily have to pick, what is the best model for the situation? You can pick fairly accurate models, run 3 different independent models, and then majority vote them. And in my own case, I've done a couple Kaggle competitions, which is a machine learning site where you can compete with other teams and try and win awards and help companies and do interesting projects. And that's been one of our techniques, is running multiple different models, which are all pretty good, and then kind of combining them together using an ensemble to get an even higher score. Okay. So that is that. I think I will end here. So let me recap kind of what we've covered, because I've covered the basic kind of model types for this level of machine learning, kind of the machine learning 101. And I'll talk about what we could do next in subsequent conversations. So just to close, so what we have been doing actually is an area of machine learning called classification. So you're trying to answer a question like, what flower is this? Is it going to rain tomorrow? Is this patient going to be at readmission or have diabetes in the next year? Those kinds of questions. Is this product based on this posting going to sell or not? Questions like that, which you're putting instances in a class. Okay. So that's, and the reason I started there, this is the most popular kind of machine learning, is classification. And essentially, you're trying to generate, using these generic algorithms, a function where it's a function of the features, determines the class, and you have a generic algorithm that you just pump in a lot of data, and it sort of generates this function, in a sense. What we covered today was linear separation, which is essentially drawing a line or a hyperplane through the space where all the features are graphed. And you're essentially learning the weights there on a linear equation. The second is decision tree separation. So you're basically working your way through the features, separating things out, and building a tree of rules that do the best job separating the classes automatically. And then K nearest neighbors. So essentially you're not really learning, you're just finding patients like this patient, or situations like this situation, or flowers like this new unseen flower, and finding what they are, and then assuming this new point is like that. So that's K nearest neighbors. And then ensemble techniques, which is essentially just majority voting them all. So using a combination of these things, and then combining them together. I'm talking about majority voting, but there are a few other techniques, but essentially combining them together to actually get a better accuracy than any of the underlying models. So I'll just mention topics that I haven't discussed, and I might do sessions on these. We'll see. So one is feature engineering. So there's actually quite a bit of work in machine learning on getting the data right before you feed these algorithms. So I have oversimplified this in this hour greatly. Okay, I've used flowers that all the fields were filled in. They were all numeric. They were all accurate, and the model works out fine. Now we don't have data like this. We have lots of nulls. We have lots of missing data, non-numeric data, lots of text, lots of things that are the same thing stored in multiple places or phrased in multiple ways, and the data is messier. And so there's this whole area of feature engineering, which is essentially where subject matter expertise comes back in, which is how to get this data in a nice, clean, structured way that can be pumped into these generic algorithms and have decent results on the other side. So that's one important topic. The second is text analysis. So again, I'm dealing with numeric data in the examples I gave. But how would you deal with documents or clinical notes or categories of things, or things where they're not numbers, but they're important factors in driving decision making? So there's a variety of techniques on how to deal with text in machine learning algorithms. And then lastly is deep learning and image analysis, which you don't have to combine together, but they often go together, which is how to set up what's called a neural network, which is a more complicated equation between the features on one side of the page and the class on the other side of the page, where instead of each of the features multiplied by a weight leading to the class, you have layers in the middle that do part of the work leading your way to the class. And I'm sure that didn't make any sense, but deep learning is also referred to as a neural network, an artificial neural network, and it's a more complicated architecture, but it's quite similar to what we've covered. It just has this few extra dimensions to the way the equations are put together, the way the weights are learned, that kind of thing. And it's almost always used with imaging, and it can be used with text and these other topics as well. So that's it. Hope that was interesting. Hope you learned something. Again, machine learning, it's a very important new way of solving problems. Sure, it's overhyped at the moment, but I think it's important. And it's really not that complicated. So hopefully you got a sense for how these algorithms kind of work, how they learn from data, and what some of the techniques that they use. And it's kind of amazing. You know, these basically simple techniques can really yield great results. So that's it. Bye-bye.